Okay, we'll go ahead and get started. Can the people on Zoom hear me okay and see my slide?
Yes.
Thank you. So what we're going to do today is first we'll go over and I'll review the quiz that you had last week, or rather earlier this week. And so we'll go over the answers on the quiz, and then we'll finish up chapter 12 today. And then I just want to remind everyone that on Tuesday of next week, you'll have your first full exam, and that'll cover chapters 11 and 12 both. So once again, that exam will be on Canvas. So once again, that exam next week on Tuesday will be on Canvas. So just as you went online for the quiz and took the quiz, you'll do the same thing with the exam. As you know, the exams are worth 100 points versus the 30 points for the quiz. So it'll be longer, more questions, more time, things like that. So, okay, so once again, we'll review quiz 1, the answers for that. Then we'll finish up chapter 12. And then on Tuesday of next week, you'll have your first full exam, which will cover chapters 11 and 12. Any questions about any of that stuff? Okay, so going through the quiz, question 1 was asking you to fill in some blanks concerning a gas and a liquid and how it goes into its container. And so the answer was a gas is compressible, and it assumes the volume and shape of the container. So remember we said you can compress gases. That's where the concept of pressure comes into play. And gases, if you put gases in a small container, it fills it up. If you put them in a big container, it fills it up. So gases expand to fit the size of the container. Whereas a liquid, it's not compressible, and it assumes the shape of a portion of the container. And so the difference there is, as I said, if you put gas in a big container, it fills the whole big container. You put it in a small container, it fills the whole small container. A liquid, if you say have 100 mils of a liquid, it's just going to fill a 100 mil portion of whatever container it is. If it's a 100 mil container, it'll fill the whole container. But if it's a 1,000 mil container, it would just fill a small portion of that. The second question, which molecule of these choices has hydrogen bonding as the predominant intermolecular force? So remember, for the answer here is CH3COH, which is methanol. The key thing there is, remember we said to have hydrogen bonding, you of course need to have a hydrogen atom, but it needs to be bonded to oxygen, nitrogen, fluorine, something like that. And that's the only one of the choices that had that hydrogen bonded to, in this case, oxygen. Number 3, when KBr dissolves in water, you get aqueous potassium plus and bromine minus ions. The force of attraction that exists between potassium plus and water is called what type of interaction? And that's an ion dipole interaction. So you have that positively charged potassium ion interacting with the negative part of the dipole on the water. Okay, and number 4, the intermolecular forces responsible for the fact that CH4, which is methane, has the lowest boiling point in this series of compounds. The reason for that is, the answer is dispersion forces. So with these types of compounds, they're all just alkane structures. And so with that, you don't have anything that is polar. These are all nonpolar molecules. Since they're nonpolar, you don't have any dipole-dipole interactions. You don't have any hydrogen bonding interactions. So even though there is hydrogen present, it's not hydrogen bonding as we define it. So that leaves just the dispersion forces. Okay, number 5. What types of intermolecular forces exist between CH3OH, which is, as I said before, is methanol, and H2O, which is water? And so we always have dispersion forces. We said that that's something that no matter what we're talking about, there's going to be some level of dispersion forces. In this case, we're going to have dipole-dipole interactions. And so we're also going to have hydrogen bonding. So we've got all 3 of those going on. Number 6, scroll up a little bit here. The shape of a liquid's meniscus is determined by what? And the answer there is the relative magnitudes of cohesive forces in the liquid and adhesive forces between the liquid and its container. And if you recall, the example that we had in class was we had mercury and we had water. And we talked about how those two, the meniscus of each of those materials was different. The water kind of goes up on the sides, the mercury goes down on the sides, and it related to those interactions within the solution and then interactions with the material of the wall. Number 7, the property responsible for the quote unquote beating up of water, that's surface tension. Number 8, which of these is an exothermic process? So remember, endo, you're putting energy or putting heat into it to make it occur. Exo, it's coming out. So the answer for 8 is freezing. And so melting, subliming, boiling, all of those require you to put energy into it for that to occur. Freezing is the one where it's exothermic, so energy is given off. Number 9, which of these substances has the highest boiling point? So if you're trying to figure out the highest boiling point, you want to go with the one that has the most intermolecular interactions. And so the diol, which is OH, CH2, 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 OH, that one you have your regular dispersion forces, but you also have 2 instances of hydrogen bonding with those OH groups on each end. So the CH3, CH2, OH, you have some hydrogen bonding going on there, but you have more of it with the other choice because there's 2 of those OH groups attached to a carbon. So that's why that one is has the higher boiling point. And then finally, number 10, I think this was probably everyone's favorite question. And so before I kind of go through the math on this, I want to just talk a little bit about what from a physical transition perspective is going on. So we talked about this a little bit in class, that we had that energy diagram that we made where we showed what happened at each of the steps, and then we'd have to calculate the energy at each of those steps. So there's a couple things you needed to be aware of to get this problem correct. One is you need to realize you're working with water, and you needed to remember that water freezes at 0 degrees C and boils at 100 degrees C. So you're going to have transitions at those 2 temperatures. And so if you remembered that, then that helped you piece it together a little bit. But we're told in this problem that we're starting at -4 degrees and we want to go up to 109 degrees. And so at -4 degrees, it's a solid, it's frozen. And so we would have that first transition from -4 up to 0 degrees C. So we'd have an energy calculation to do for that transition. Then once we're there, we've got to convert all of it to liquid. So there'd be a transition energy calculation to do for that transition as well. Then we would go from 0 degrees up to 100 degrees C, because remember that's the boiling point. We'd have an energy calculation for that change in temperature. And then once we get to the 100 degrees, we've got to convert it all to gas, to steam. And so then there's a calculation there for that transition. And then finally going from 100 degrees to 109 degrees C is the final calculation you would need to do. So we wanted the answers in kilojoules. So some of these constants that were given are in joules. So you'd have to make sure that you successfully got that transferred over to kilojoules. And then calculate each of those different energy changes that you'd need, and then add them all up to get the right answer. So, like I said, I think a key thing is just thinking a little bit about what those transitions are and what you would have to do to get there. So, okay, here's the math of it. And once again, all this stuff is posted on Canvas. So if you want to take a look at it later when you have a little more time, you can. So one of the first things I did was just calculate the molecular weight of water. Have 2 hydrogens, so that's 2, 1 oxygen, that's 16 for a total of 18. And then I did my first calculation for that transition from -4 to 0 degrees. So at 25.0 grams of water, I'm given my constant of 2.09 joules per gram Kelvin. And then that delta T there from -4 to 0 is a 4-degree difference. So if I go ahead and do that math, I get 209 joules. Converting that to kilojoules, it's 0.209 kilojoules. So now I want to do the energy calculation for transitioning that solid to water at 0 degrees C. So here's where my molecular weight will come into play. 25 grams, I want to convert that to moles. Then use my next constant, which is 6.01 kilojoules per mole. And I get a value of 8.35 kilojoules there. So I've gone from -4 to 0 degrees. I've changed the solid to liquid. Now I want to go from 0 to 100, because as I said before, I needed to remember that 100 degrees C was my boiling point of water. So 25 grams using the constant for this transition, 4.18 joules, grams Kelvin. That temperature difference is 100, and I get 10,450 joules, or 10.4 kilojoules. Now that I'm at 100 degrees, I'm going to do the transition from liquid to gas. 25 grams divided by 18 grams to convert to moles. And then I use that next constant, 40.67 kilojoules per mole, and I get a value of 56.5 kilojoules. And then the final step is I'm at 100 degrees. I've converted everything to gas. Now I want to heat up to 109 degrees. So that change in temperature is 9 degrees. So I have 25 times 1.84 joules gram Kelvin times that delta T, which is 9. And I get 414 joules, or 0.414 kilojoules. So now I've calculated all my individual steps in the process. So what I would do is I would simply make sure all those are in kilojoules, because that's what I want my answer in. And I would add those up, and I get a value of 75.9 kilojoules. So any questions about anything on the quiz? Okay, so this one nice thing about having the quiz is you kind of get a sneak peek at what the kind of problems will be on the exam for this chapter. And so what you saw on this quiz is that the first 9 questions were more about the theory and concepts, and people did pretty well on that, so congratulations on that. The last question was actually doing that heat calculation, that energy calculation, And so people didn't do quite as well on that. I guarantee you there will be another problem, at least one, similar to that. It probably won't be water or be the exact same thing, but it'll be along that lines. So if you got it right, great. If you didn't, go back and take another look at it, take a look at the calculations, but more importantly, make sure you're comfortable understanding the different transitions and doing that calculation, okay? All right, let me pull up the chapter 12 slides and we'll work on that. Okay, so what I'd like to do is finish off the solid stuff with the covalent network solids. And we talked about this a little bit last time. Covalent network solids are where you have these covalent bonds that go from atom to atom across a network. And the result of that is you get some unique properties. And one of those is things tend to be pretty strong. And the example that we talked about was diamond. And so in this case, each of the carbon atoms is covalently bonded to other carbon atoms. And we know that covalent bonds are pretty strong bonds. And so what that results is the carbon in a diamond, that configuration, that covalent bonding network results in it being a really hard material from a physical strength perspective. And it has a real high melting point. So that's kind of a common theme in these covalent solids. So another one that is real common are semiconductors. And with semiconductors, to understand that, we need to think back to molecular orbital diagrams. Okay, so we're not going to get real involved with the molecular orbital diagrams, the nitty-gritty of it. But I think the general concept I just want to remind everyone of what we've talked about. So in this diagram, we see the atomic orbitals on the left and right, where we see s orbitals, p orbitals. And in the middle, in this lower one, kind of bluish box that says valence band, and the one up on top, conduction band. What those are representing is the blue one labeled valence band is representing bonding molecular orbitals. Remember, we talked about that. And the one on top, the conduction band box, that's representing anti-bonding molecular orbitals. And so if we drew all those molecular orbitals out, we would have as many molecular orbitals as we have the atomic orbitals that are involved. But in this case, and we talked about this a little while ago, after a while, these things start to get kind of smeared together. And so we're not going to worry so much about the individual ones. But we're going to lump it into this occupied bonding down at the bottom and the unoccupied anti-bonding on top. And so this distance, this energy distance between what we call the valence band and the conduction band, that's known as a band gap. And there's energies associated with that. And depending upon what that energy is, if it's a low enough value, then it can be a semiconductor. And there aren't a lot of materials that can be semiconductors, but there are a handful, and we'll talk about what those are. And so the way this works is you have this gap. And so in order for electron transfer to happen across in the material that you're talking about, this band gap energy value must be low enough so that electrons can go from the valence band up into the conduction band. And the elements that you see that in are the group 4A elements, in particular, silicon, germanium, and tin. So those elements, when you draw out their molecular orbital diagrams, they have band gaps that range anywhere from 0.08 to 3.05. 3.5 is kind of the magic number and the energy for that band gap. If you get above 3.5, then you don't get the electron transfer across there, and the material essentially becomes an insulator. And so this is why if you ever hear about chips, microchips in computers and stuff like this, it usually has like silicon, you always hear about silicon wafers, right? Silicon, germanium tin, things like that. But this is the reason why, because it goes back to this band gap thing. And these 4A elements, and like I said, these are the three ones you hear a lot about in 4A. They have that band gap energy low enough so that this transition can occur. One of the key things about the 4A group, if you recall, if we think about where they are in the periodic table, that's that 4A column, we have 4 valence electrons. And that tends to be a pretty common thing in order for this to happen is you have 4 valence electrons involved. What you'll see is that there are a combination of elements that people use to make these semiconductors also. And then you start getting away and having some additional elements, not just the 4A. But what you usually find is that the average of them will be 4 valence electrons. And so in this one, gallium with arsenic, so gallium arsenide, gallium has 3 valence electrons, arsenic has 5, so it averages out to 4. So when you form that molecular orbital, okay, you wind up with the proper number, in other words, 8 valence electrons to kind of put into the molecular orbitals. And so here is some information about semiconductors. We see the material on the left. These semiconductors usually are blends where they have a couple of different atoms involved. And we'll see in a little bit some slides that talk about why that is. But the big thing here is seeing these band gap energies, this EG column. And we see those are all pretty low. And so that's what we said before is, in other words, for that, to be able to make that transition based on our molecular orbital diagram, we need that band gap energy value to be below 3.5. And these are all well below 3.5. Okay, I mentioned before that a lot of times it's not a single element material. And this is where the concept of what's called doping comes into. And so we see some examples here where on the left picture, we see our valence band down at the bottom, our conductance band at top, and then we've got that band gap energy. By introducing an impurity, and this is where the concept of doping comes into play, by introducing an impurity into it, we can change this valence band of how it is. We can have something called an N-type semiconductor, where we have extra electrons and electrons start to go into that conduction band, or we can have P-type semiconductor and we have less electrons, and so we have some empty molecular orbitals down in the valence band. One easy way to remember that is N-type. If you have extra electrons, it's going to be negative, right? Because electrons are negative, so if you've got extra, negative. So I always think N, negative, extra electrons to get to the negative. And then P, I think positive. If something's positive, it's lost electrons. So that's my way personally of remembering what is N-type and what is P-type mean. And sure enough, in our definition over there for N-type semiconductors, we say that N-type semiconductors have more electrons in negative, because the electron is negative. And so now we've got some charge up in the conduction band. So that negative charge is able to travel into the conductance band. P-type semiconductors, once again, if it's P, I think positive. Positive means I've lost some electrons. So in that case, we create what they call a hole in the valence band, and then you now have a loss of electrons, a lack of electrons there. So, okay. So how does this all fit into like the real world? So one way it does is with photovoltaic cells. And so photovoltaic cells are something that are pretty common. So if you're like me and you have a calculator, it doesn't have a battery. I never have to replace the battery, but it has that little strip on top, which it has to have light shining on it in order to have energy to power the calculator. That's a real simple example of this N-type, P-type stuff. And so on these drawings that we have here, in this case, it's silicon and arsenic, all right? So in this case, the arsenic brings an extra electron into the situation. And so that's an N-type of doped semiconductor. On the right-hand side, we have a P-type, and in this cartoon, we see the boron here in the middle, and boron has one less electron, and so we see a gap there. That's that hole, so to speak. And so the nice thing about these photovoltaic energy cells is that in this case, you have energy hitting it in, and on those calculators, the energy is the sunlight. And then it causes movement, depending upon which type you have, of electrons. And so the nice thing about this is there's no moving parts, there's no noise, there's nothing like that. And so that's an example of this p-n junction type thing comes into play. Another example is you can have bigger of these cells. And so if you have an N-type silicon sample and have it in contact with a P-type of material, then that's called a p-n junction. Once again, the light hits it, and that excites electrons, and it causes them to flow from the inside to the P side, right? Because the inside, we have the extra electron. It wants to move to the other side. And then as these electrons move through that junction, that's where you get that's how you get your energy. So it comes off of the original energy source is the light. And so these are examples of how, like I said, for me, I think of it more in terms of that little pocket calculator that I have, that I never have to buy batteries for and have had for 10 years. And all it needs is some sunlight. It's based on this NP junction stuff. So going back to what we said here, on the semiconductor thing, talking about the doping results in N-type and P-type semiconductors. Kind of had a cartoon here of what the atoms would look like next to each other, seeing the hole and versus having all the electrons filled. And then a couple examples here of how that junction of having the P and N-type layers stuck next to each other would pay off. So when you get to like computer chips and all that, obviously that's more sophisticated than what we're talking about for a pocket calculator, but the general idea is kind of the same. It gets back to that having materials, that gap in the molecular orbital diagram, the energy is low enough that you can overcome that. And then kind of playing with the materials a little bit to make it more likely to have electron flow if you do get a little bit of energy going in. Any questions on that? Okay, so there are a few homework problems associated with this last section that we did. And one of them that I want to spend a little bit of time on is 12.59. So let me grab that. Okay, so in 12.59, we have manganese sulfide, MnS, and it tells us it has a rock salt structure. And so if we went back and looked in our notes or our textbook, we would know that a rock salt structure, rock salt is sodium chloride. So that was one of those 1-to-1 atom ratios. We remember that that's a face-centered cubic lattice, okay? And so then it asks us some questions. If the length of the edge is 5.223 angstroms, what's the density in grams per centimeter cubed? Okay, so the first thing we're going to want to do, at least for me, if I know the edge length, okay, and that's the 5.223 angstroms, I'm going to want to go ahead and convert that into centimeters. And so I need to remember that an angstrom is 10 to the minus 10th meters, and that a centimeter is 10 to the second centimeters equals 1 meter. So 100 centimeters are in a meter. So I do that first calculation up at the top where I converted using dimensional analysis my angstroms to centimeters. Then I think about that, what it told me it's similar to rock salt, which is sodium chloride. And I remember on that 1-to-1 atom ratio, that's a face-centered cubic lattice. If it's a face-centered cubic lattice, I want to go ahead and calculate how many of those atoms I have. And I can go ahead and I can calculate sulfur, which tells me it's 8 times 1/8 equals 1, 6 times a half equals 3, so a total of 4 atoms there. The manganese, 12 times 1/4 equals 3, and then 1 times 1 is 1, so a total of 4 there. So I know for each of those, I have 4 atoms of sulfur and 4 atoms of manganese based on what I know about the shape and things like that. So now what I want to do is I want to change each of those number of atoms into grams. Because remember, I want density, and density is going to be grams per centimeter cubed, so weight per volume. And so if I have atoms, if I have 4 atoms of sulfur, I can convert that to moles of sulfur using Avogadro's number, which is 6.02 times 10 to the 23rd atoms per mole. Then once I have that in moles, I can use the atomic weight of sulfur, which in this case is a little over 32, to convert it to grams, and I get a gram value for sulfur. I do a similar calculation for the manganese. So I convert those 4 atoms of manganese into moles of manganese using Avogadro's number. Once I do that, then I convert it into grams using the atomic weight of manganese, and I get a value there. I add up those 2 numbers. That'll be my total mass. That'll be the mass from the 2 atoms that are involved in this compound. And then I want to divide it by volume. Well, up in the very beginning, I converted my edge length into centimeters. And for a cube, it's length times width times height, because all those are going to be the same since it's the cube. And so if I take that number that I had up there and expressed in centimeters, my denominator will be centimeters cubed. And so I remember that volume can be mils, but it also can be centimeters cubed. And so by then adding up the two weights that I got and dividing by that edge length cubed, my units will be grams per centimeter cubed. And in this case, the answer is 4.06. So for this kind of problem, the things I needed to do is I needed to be aware that I needed to be able to calculate the mass of the atoms involved, and I needed to be able to calculate the volume of the cube involved, because I knew it was a face-centered cubic lattice. So based on that geometry and what I knew about that, I was able to figure out how many atoms of each were there. And so if you don't remember how to do that, you may need to go back and look at your notes or look at the textbook and see that calculation, but you wind up with 4 of each. Once I have the number of atoms, then it's a conversion using Avogadro's number and the atomic weight to get it into grams for each of those. And then finally, it's ratioing that grams over the volume. Okay? Any questions on this one? So let's move on to another type of material, which is known as polymers. And so polymers, usually when people think of polymers, they think of plastics. And that's usually pretty much the same thing. And so polymers are just molecules that have high molecular weight, okay? And so they are made, though, by joining small molecules together, and then that tends to repeat over and over and over. And so those small molecules that are joined together are called the monomers. And as I said before, plastics are the most common kind of polymer that people think of. So there's a whole bunch of different types of plastics out there. If we look at this, let's take a look at this table for a minute, because this is something that you probably are aware of. If not, let's talk about it a bit. And so this goes to plastics recycling. So on the left here where it says number 1, 2, 3, 4, 5, etc. If you ever look, and if you have a plastic bottle with you now or nearby, you can look on it and it should say a number. Okay, and that little number, and it kind of shows you what a lot of times it looks like here in this photo down at the bottom. But it's usually this triangle with a number in it. That is the recycling code, okay? And different communities have different regulations on this. Almost everybody takes 1, 2, 3, 4. I mean, once you get past that, some of these others, some places take it, some people don't. But what that code is, it tells you what kind of polymer it was. And sometimes they'll even have the abbreviation. HDPE is one you see a lot, high density polyethylene. LDPE is low density polyethylene. So over on the right here is the name of the polymer that was involved. So you always have the number, you might have the abbreviation, you never have the name. I rarely ever see the name written. But this is the code of what it is. And based on, like I said, the community you live in, they'll let you know if they recycle any of this stuff. And so that's why if you have plastics, you want to take a look at the number before you put it in the recycling bin to make sure that it really is one that they take. Because if it isn't, then it's kind of a pain in the neck for them to sort it out and remove those others. So there's different types of plastics. There's thermoplastics, and these are ones that can be melted and reshaped. And when you thermoset something, it's usually an irreversible chemical reaction. And so you do the reaction, you get the property you want, and then that's pretty much it. But there's another thing called elastomers, and elastomers, you can usually tell if it's an elastomer because it tends to be rubbery. And so you can bend them and stretch them and things like that. if you think about plastics, we use that as kind of a generic term, but there's really a lot of differences in them. Even on these ones here that we talk about with recycling, some of them are pretty, you can bend them and all that and they don't break. Others are pretty brittle and you can snap them and stuff. After you spend a little bit of time looking at the numbers, you start to get a little better feel for which are which. But plastic's a generic term. Within the polymer industry, there's a whole bunch of different types, and these polymers are made to give certain, whether they need something that's strong or something that's bendable or things like that. So the polymer will be designed to get the property that they want. When you make polymers from an organic synthesis perspective, there's two main types. There's what's called addition polymers and then condensation polymers. An addition polymer is just kind of what it sounds like. You have your two monomers. It's often the same molecule, and then you just keep combining them over and over and over and over, and you just keep adding to it. That's where the term addition polymer comes into play. Condensation polymers, when you think of condensation, what do you think of? You think of water. So condensation reactions are reactions that when you do the reaction chemistry, you change the structure of the monomers a little bit, and the result is they lose a water molecule, and then there's a bond formed where the H, the two H's and the O have been. And so that's the idea behind condensation polymers. So here's an example of that addition polymer. So in this case, we have ethylene. Ethylene is a pretty common starting material in the polymer world. And so what you see here is you have that double bonded carbon to the other carbon. And so what that means, you got a lot of electrons there, kicks out some of those electrons, and you wind up, in this case, forming polyethylene, which is just a long chain of CH2, CH2, CH2 on down the line, okay? So this is the addition type of polymerization reaction, where you just keep adding on. And depending upon how long that chain is, you get different physical properties and stuff like that. For the condensation polymerization, in this case, we see we've got two different molecules. We don't know what they are because they don't give us the rest of the structure, but we see on the left here that the nitrogen and the two hydrogens and then something else to it. So we have an amine, that's an amine group. And then on the other side, we have carbon double bonded to an oxygen, single bonded to an oxygen, single bonded to a hydrogen. That's called a carboxyl group. That COOH is a carboxyl group. So we have the carboxyl, the OH from the carboxyl group, combining with the hydrogen from the amine group, and then we get a new compound plus water. So that's the condensation part. We've kicked out water on that reaction. So in this case, this reaction would happen over and over, and you'd get a long repeating chain of this resultant molecule that we see here. When you have two different monomers like this is then the resultant polymer is called a copolymer. And copolymer just means that unlike this ethylene polymerization, where it was ethylene reacting with ethylene, so the same thing all the time, here we have two different compounds reacting to form our polymer. And like I said, when that happens, you call the result a copolymer because it's from the addition of two different monomers. So a whole bunch of polymers are out there, as I said. Here's just a handful of them. This is more just for your information, your interest. I'm not going to ask you to memorize this or anything. But what I think is interesting is on the left-hand side, you have the name of the polymer. In the middle here, you have the structure of what the single unit is. this little N here, so the way this is expressed is, you see the little N in the lower right-hand corner of the brackets here, and that is how many of those units repeat. So it could be 5, it could be 10, it could be 50, it could be whatever. In that case, you would see this molecule, or this portion of the molecule that's in the brackets, just repeated over and over and over and over. Okay? And then in the brackets, you see that, like on the one on the bottom, the PVC, we see the CH2 and the CH, we see a line, a bond representing a bond, go through the brackets. That's telling us that's where it would attach. So on this CH with the chlorine on it on the right-hand side, that CH would then attach to a CH2, which would have a CH and a chlorine, and then that would attach to a CH2, CH chlorine, and on down the line. So this is the standard way that people describe polymers, where they put in whatever the repeating unit is in parentheses of some kind, and then they have that little N there to tell you how many of those you need to draw after it. The other interesting thing about this table is it kind of tells us on the right-hand side what it's used for. So if we look at the bottom one, polyvinyl chlorine, PVC, we see that it's used in pipe fittings and plumbing, whereas we see polyethylene up on top that tells us it's used for films, packaging, and bottles. So which do you think is a stronger polymer, PVC or polyethylene? Just if you had a guess.
PVC.
Yeah, why do you say that?
Because it needs to be strong for the plumbing.
Right, so she said she thinks PVC would be the stronger of the polymers in terms of physical strength because it's used in pipe fittings and plumbing. And you're 100% correct. And so you wouldn't want something that's used for films and packaging because that's going to be pretty very easy to manipulate, and you're going to easily cut it because you want to cut open that packaging, right? You wouldn't want that with your plumbing or you'd have a big mess. So with each of these, it kind of shows you with these types of polymers what it's used for. And here's some continuation of this, of some addition ones. So polyurethane, the top one, that's the foam stuff in your furniture. That's polyurethane. And here you can see what that polymer structure would look like. One thing I will point out, if you look on this one, you see on the left-hand side a capital R, and then an R with a accent on it, so R prime. And I know you're thinking to yourself, there's no element that's R. Well, R in this type of nomenclature and in organic chemistry in general, R means some type of functional group. And they're telling us here that in this case, R and R prime could mean something like CH2, or some other functional group. Once again, why don't you just write it out? Well, people are always looking for shortcuts, is the easiest way to explain that. So we see a phthalate here on the next one, nylon, and a polycarbonate. And so once again, on the right-hand side, if you're interested, some examples of things that are made out of those polymers. And this is just a small portion of them. It's just meant to give you a feel for what the polymers are used, how different the structures are. You know, the simplest one is that polyethylene, which is just that ethylene. Remember, we talked about adding ethylene group to ethylene, getting rid of that double bond, creating single bonds. That's pretty simple. Some of these others, as you go along, get more complex. And once again, that gets to imparting whatever physical and chemical properties you're interested in. So when we talk about the bulk properties of polymers, we said that polymers are really long, like a really long chain. So these are big molecules. And so you can even think of it kind of like a rope. And so the thing is, just like a rope isn't just perfectly straight, the polymers kind of move around to and twist and bend and things like that. And the longer it is, the more of that lack of structure you can have. So the other thing a lot of times you find with polymers is when you do the reaction, you don't get everything with that same number of N on there. So in other words, remember we said that little N subscript told us how many of these units are strung together. It's very common for polymers to have a range of molecular weights there, and that's just a function of the chemistry. And so you get some varying lengths of chains. You start to get some twisting, bending, and all this. And that's one reason why a lot of the polymers are pretty pliable, pretty bendable, pretty, you can manipulate them pretty well. Well, sometimes that's great. If you're making saran wrap or plastic wrap to put over your food, you want that to have that. Some other instances, you don't want that. And so that gets into trying to introduce some order into polymers. So we're talking about solids. And as we've talked about solids, we've said which ones are the most crystalline, which ones are the hardest, so to speak. And those are the ones that had these really well-defined crystal structures, right? One of the best ones was those salts. The other really good one was the covalently bonded solids. But what those things had in common, though, was really well-defined structure. And well-defined structure means order. So the same is sort of the same thing in polymers, is you'll have regions where things will line up really well. Okay, and that's some examples here, the circles that are outlined on the figure. Those are areas where they're pretty well ordered, and in those areas, you say that there's some crystallinity to it. And you say that just because of the order. Once again, we said that crystals, one of the defining things about them is they have good order. And so that's where this term kind of comes from. As you get more of this order, the polymer tends to get denser, tends to get harder, more resistant to heat. Kind of the same stuff you expect out of a crystal or that covalently bonded solid, things like that. Order in molecules tends to give it strength. And so in the polymer world, sometimes you can give it even more order or more strength by doing something mechanical to it. So if we have said we want all these to kind of line up on top of each other like it looks in the ordered regions in the diagram, you think about it, we got these long strings, so to speak. If you start pulling those out mechanically, they line up better. So that's one way of doing that. When we talk about the crystallinity, here we see percentage of crystallinity going from 55% to 85%. So in other words, increasing that order for whatever polymer this is. Okay, in this case, it's polyethylene. And what we see is that melting point goes up. Melting point, think about it, goes up because now you're going to have more order, things are going to fit together more, you're going to have more interactions. The more interactions you have, the higher the melting point. We see the density goes up a little bit, not a lot. Stiffness and yield stress both go up. So stiffness is just what it is, what you would think. If it's stiff, it's just a stiffer material. Yield stress, that's a measure of if you put pressure on it, you stress it, does it break? Does it bend? Does it have some physical change? When you do those yield stress type tests, it's usually measured in something called PSI or pounds per square inch. So if you think about pounds per square inch, what you're talking about is the amount of pressure on 1 inch of material. And so the higher the number, the more it can handle before it fails, however you're defining fail for that material. There's another way to change the physical properties of polymers. And that is to have, you have your change and then react the chains with each other. And so in this case, the top figure, if you look at the little red, what looks like those are supposed to, I guess, represent bonds in the chains. So a lot of times, and in the bottom here with these sulfur atoms, you see a better example. You have two chains and you have these sulfur atoms, and you can react the sulfur together to get a bond there. So you take, the general idea behind this is to take some functional group in one of the polymers and react it with a functional group in the other polymer. So then they kind of stick together. And that'll give them, that'll typically give you a stronger situation. And this is called cross-linking. Okay, so under this vulcanization thing, you see here chains are cross-linked. Cross-linking is a real common thing in the polymer world. And when you do the cross-linking, it's almost always to give it some type of physical property that relies on you want it to be stiffer or stronger or something like that. And that goes back to when we were talking about here, the typical polymers don't have maybe as much order as you would want. And if you want a stronger material, you'll do that cross-linking of the polymers. Okay. Before we move on to nanomaterials, any questions about the polymer part? The things to remember there, polymers are just large molecules. They have repeating units to them. So whatever those monomers are, they repeat over and over and over. If it's the same monomer over and over, that's one form of polymer. Sometimes you have copolymers where you have two monomers, two different monomers that are reacted, and then that result of that reaction repeats over and over. We talked a little bit about strength of it and some things you can do to improve the strength, and that gets back to that crystallinity. It gets back to cross-linking. But the common thing in both of those is that to add strength to polymers, you're basically trying to increase order in that material. And if we think about that, that makes sense, because when we talked about covalently bonded atoms, that had a lot of strength, a lot of order. We talked about crystals, the ionic crystals, that had a lot of order, a lot of strength, things like that. So it kind of goes hand in hand. Okay, so nanomaterials are relatively new. You may hear about them in the news sometimes, so we want to talk just a little bit about it right now. And so the general definition of nanomaterials is that they're in the 1 to 100 nanometer size. And remember, nanometer is 10 to the minus 9th meters. So they're little, okay? So these are little materials. And as I said, nanomaterials have been in the news quite a bit the last few years. So we just want to talk a little bit about what it is. We know from theory that 1 to 10 nanometers is equal to about 10 to 100 atoms. And so we're really talking about little stuff, right? And you may have heard something called quantum dots. And so quantum dots are just semiconductors that fall into this 1 to 10 nanometer size. The other thing about the quantum dots is if we look at the figure on the lower right-hand side, we see our old friend band gap energy, okay? And we talked about that being important in terms of getting that electron flow to go. And with these quantum dots, which is why they're looking at them in terms of semiconductors, is that you think about it, if you're building a computer or something like that, you want things as small as possible in order to to just have less weight, less size, things like that. So if you could take advantage of these really small quantum dots to make your semiconductors on that, then you would get some of those benefits. Another thing that's come about in the last 20, 30 years is we always knew about graphite and we knew about diamonds, right? So graphite is the thing that's in your pencil, relatively soft. You can press on it, break it pretty easily. Well, that's carbon. You look at diamonds, which we've talked about a bit. Once again, that's just carbon. So graphite, diamond, same thing. Just that structure is different, which results in one of them being really strong, one of them being not so strong. About 25 years ago or so, maybe longer, well, it was the 1980s, so 30 years ago, another form of carbon was found, and it's this thing called buckyballs. Okay, so on the right here is what it looks like. So remember what the diamond shape looked like. This is a different configuration of carbon atoms. It's typically considered to be a C60. So in other words, this ball that you see, each of these kind of corners represents a carbon atom. And there's a total of 60 in there. And so, so these buckyballs was a new form of carbon that was discovered. At the time, this was a real big deal. I remember when this happened. And so people have done some stuff with it. And after they found it, they thought, well, this is really cool and great, but what do you do with it? Well, it's taken quite a while for people to figure out what to do with it. But really what has happened is they figured out how to manipulate, as chemists have figured out how to manipulate those buckyballs, it's led to carbon on a nanoscale. And the big one is this second bullet point here, carbon nanotubes. And so what they found is it can be made with metallic or semiconducting properties without doping. That doping process we talked about where you put some other atom in there, that's not simple to do. Okay, so if you now can have some material where you don't have to do the doping, but yet you can get different properties, that's a big deal. And so what came out of that buckyball stuff was this carbon nanotube stuff where they figured out ways to manipulate it. And as they did that, they got some physical properties and some electrical properties that had benefits. So there's a few questions about this stuff. When we talk about, to be honest, when we talk about the carbon with the buckyballs and nanotubes and stuff, we talk about the nanomaterials. Those are there just so that you're kind of aware of them and kind of see some of the uses of this kind of stuff. Polymer stuff is just showing you once again another type of material that you can have that really you encounter every day in life. Polymers are everywhere. And as time goes on, there's good and bad of that in terms of pollution, but also in terms of just reality of what we need to live. And then finally, the other thing is we talked about is the hard materials, not the molecular solids, but the covalent network solids, which was diamonds and the semiconductors and things like that. So that's all I have for today. I just want to remind everyone that on Tuesday of next week, we have our first full exam, and that will cover chapter 11, the one we just had the quiz on, and it'll cover chapter 12, which is what we just finished today. So once again, go on Tuesday next week, go into Canvas, pull up the exam, take the exam, and then I'll see you in class again on Thursday of next week. Any questions before I sign off? Okay, thank you.